How do spacecraft actually move through space? When you imagine a spacecraft far from Earth, the picture is usually one of perfect emptiness. No air, no wind, no ground. Just a machine floating in darkness, surrounded by nothing at all. From that image, it feels natural to assume that movement must be impossible, because in everyday life, movement always seems to require something to push against. Yet spacecraft do move, and they do so with remarkable reliability. They travel across vast distances, adjust their paths, rendezvous with planets, and arrive at precise destinations years after launch. All of this happens in an environment that appears, at first glance, to offer nothing that motion could work with. If you enjoy calm explorations like this, you're very welcome to like and subscribe, and if you feel inclined, I'd love to know where you're listening from right now, wherever in the world that happens to be. The confusion comes from how strongly our intuition is shaped by life on Earth. Nearly every moving object we encounter is surrounded by forces that slow it down. Air presses back, surfaces rub, energy is constantly drained away. When a car stops accelerating, it slows. When you stop pushing a box, it comes to rest. Motion feels fragile, temporary, and dependent on continuous effort. Space removes almost all of that interference. There is no air to resist motion, and almost no friction to drain it away. As a result, motion behaves very differently. Instead of fading, it persists. Instead of needing constant input, it simply continues. This leads to a quiet but profound shift in perspective. Spacecraft are not struggling to move through space. They are not fighting emptiness or searching for something to push against. The real mystery is not how they keep moving, but why we ever thought they would stop. Once that misunderstanding dissolves, the behavior of spacecraft stops feeling strange. Motion in space is not an exception to the rules we know. It is the purest expression of them, revealed only when the usual distractions of friction and resistance finally fall away. Once that misconception loosens its grip, the behavior of a spacecraft begins to feel less surprising and more inevitable. When a spacecraft has finished firing its engines and settles into open space, it does not slow down. There is no gentle braking, no gradual loss of speed. It continues forward, carrying its motion with it, moment by moment, because nothing is there to take that motion away. This is where inertia quietly becomes the central character. Inertia is the simple tendency of matter to keep doing what it is already doing. If something is still, it remains still. If it is moving, it keeps moving in the same direction at the same speed. In everyday life, this rule is almost invisible, constantly overwhelmed by friction and resistance. In space, stripped of those influences, inertia finally speaks clearly. You can sense this by imagining a single push given to an object on a perfectly smooth surface that never ends. The push matters only once. After that, the motion belongs to the object itself. A spacecraft is no different. After launch, most of its journey is spent not under power but in silence, simply preserving the motion it already has. This changes the role of engines entirely. Engines are not what keep a spacecraft moving. They are tools for change. A brief burst of thrust alters speed or direction, and then the engines shut down again. Inertia carries the spacecraft onward, faithfully maintaining whatever motion it has been given. As a result, spaceflight becomes an exercise in precision rather than persistence. Long stretches of travel require no effort at all. They rely on the universe's natural tendency to let motion continue. In the near frictionless vastness of space, Doing nothing is often exactly what allows a spacecraft to go exactly where it needs to go. Once inertia is allowed to carry a spacecraft forward, the remaining question becomes very focused. If engines are not needed to keep moving, what exactly do they do when they turn on? The answer begins with a shift away from the idea of pushing against space and toward the idea of exchanging motion. Centuries ago, Isaac Newton recognized that motion changes only when there is an interaction. Nothing moves itself forward in isolation. Instead, motion is transferred. When a spacecraft fires its engine, it is not pressing against emptiness. It is throwing something away. Inside the engine, propellant is heated and expelled at enormous speed in one direction. That expelled mass carries momentum with it. Because momentum must be conserved, the spacecraft gains an equal change in momentum in the opposite direction. The spacecraft moves forward not because space gives it something to push on, but because the spacecraft gives something up. A useful way to picture this is to imagine standing on frictionless ice while throwing a heavy object. As the object flies away from you, you slide backward. You are not pushing against the ice or the air. You are exchanging motion with the object you released. The same principle governs every rocket ever built, whether it launches from Earth or fires in deep space. This insight dissolves the final piece of confusion. Spacecraft engines do not need air, walls, or ground. They carry everything they need to move within themselves. Fuel and oxidizer are not there to feed motion continuously, but to be expelled in carefully controlled moments, reshaping the spacecraft's state of motion. Once this is understood, propulsion becomes less mysterious and more elegant. Movement in space is not a battle against nothingness. It is a quiet accounting of momentum, where every change is paid for by letting something else go. Once motion is understood as an exchange rather than a push, the rocket engine itself comes into focus as a very specific kind of machine. It is not designed to grip space or press against it. Its only job is to throw mass away as efficiently as possible. Inside the engine, stored propellant is transformed into an extremely fast-moving stream of particles. They rush out the back of the spacecraft at speeds far greater than the spacecraft itself could ever reach. Each particle carries momentum with it, and together they form a directed flow of motion leaving the vehicle. As that mass departs, the spacecraft responds. Not dramatically, not instantly, but precisely. It gains a change in velocity in the opposite direction of the exhaust. The faster the exhaust is thrown away, and the more mass that is expelled, the greater the change in motion the spacecraft receives in return. This is why rockets look the way they do. Their towering fuel tanks are not about sustained thrust through space. They are about carrying reaction mass. Most of a rocket's launch weight is not the spacecraft at all, but the material it plans to discard. Motion is purchased by letting go. What makes this especially subtle is that the effect accumulates. A rocket does not need to shove itself forward in one decisive moment. Even a gentle, steady stream of exhaust, released over time, can build up enormous speeds. Each moment adds a little more change, layered carefully on top of the last. Seen this way, rocket propulsion is remarkably calm. There is no drama in the physics itself, just a steady bookkeeping of momentum, where every adjustment in speed is balanced by something quietly vanishing into the darkness behind the spacecraft. Once a spacecraft has been given motion and its engines fall quiet again, it might seem like its path should be a perfect straight line, extending endlessly through space. In principle, that is exactly what inertia would prefer. But space is not empty of influence. Even when engines are off, something is always present, gently reshaping the path. That influence is gravity. Every massive object bends the motion of things that pass nearby, not by pulling them abruptly, but by steadily redirecting them. A spacecraft moving past a planet is not suddenly grabbed or yanked. Instead, its straight-line motion is slowly curved, moment by moment, by the planet's gravitational presence. This is why trajectories in space are rarely straight for very long. A spacecraft leaving Earth immediately feels Earth's gravity fading behind it, while the Sun's gravity takes over as the dominant influence. Later, as it approaches another planet, that planet's gravity begins to matter more. The path becomes a smooth, continuous curve shaped by these overlapping influences. A useful way to picture this is to imagine rolling a marble across a gently sloped surface. The marble wants to keep moving straight, but the slope continuously redirects it. Gravity plays the role of that slope, guiding the spacecraft's motion without stopping it. What matters most is that gravity does not cancel inertia. It works with it. The spacecraft keeps moving forward, but its direction is constantly being adjusted. Speed and direction become separate ideas. The spacecraft may keep the same speed while its path bends gracefully around massive bodies. This is why spaceflight planning looks less like drawing straight lines and more like drawing arcs. Engineers are not fighting gravity to force straight paths. They are using gravity as a shaping tool, allowing natural curves to carry spacecraft exactly where they need to go, with minimal effort and maximum elegance. As gravity gently bends a spacecraft's path, a remarkable situation can emerge. If the spacecraft is moving sideways fast enough, gravity never pulls it straight down into the planet. Instead, the surface of the planet curves away beneath it. The spacecraft is always falling, but it keeps missing the ground. This is what an orbit really is. Not balance, not suspension. Continuous freefall wrapped around a curved world. The spacecraft is constantly being pulled inward by gravity, yet its sideways motion carries it forward just fast enough that the fall becomes a loop rather than a collision. You can picture this by imagining throwing a stone across Earth. A gentle toss makes it land nearby. A harder throw carries it farther before it hits the ground. If you could throw it fast enough, the ground would curve away beneath it as quickly as it falls. The stone would never land. It would circle the planet instead. In orbit, there is no force holding the spacecraft up. There is only motion forward and gravity downward, locked together in a precise relationship. The spacecraft feels weightless not because gravity is absent, but because it is falling freely under gravity at all times. This understanding reframes orbit completely. Spacecraft are not hovering above Earth or gliding around it. They are perpetually falling, tracing curved paths dictated by speed, height, and the mass of the body below them. Change any one of those, and the orbit reshapes itself. Seen this way, orbit is not a special region of space. It is a condition of motion, a delicate agreement between inertia and gravity, where falling never quite finishes, and forward motion never quite escapes. Once orbit is understood as continuous free fall, a subtle distinction begins to matter more than almost anything else in spaceflight. Speed and direction are not the same thing. On Earth, they are often tangled together. To change direction, you usually slow down. To speed up, you often feel a push forward. In space, these intuitions separate cleanly, and that separation is one of the most powerful tools spacecraft have. A spacecraft in orbit already has a great deal of speed. It is moving sideways around a planet at thousands of kilometers per hour. That speed is not excess. It is exactly what keeps the spacecraft from falling straight down. But the direction of that speed is just as important as its magnitude. A small change in direction, even without much change in speed, can completely reshape the path the spacecraft follows. This is why spacecraft do not rely on dramatic bursts of thrust to get where they are going. Instead, they make small, carefully timed adjustments. A brief engine burn, lasting seconds or minutes, can rotate the spacecraft's velocity slightly. That tiny nudge may feel insignificant in the moment, but over time, it grows into a vast change in position. The reason lies in accumulation. Motion in space compounds. When a spacecraft's direction is altered just a little, that new direction persists. Every second afterward, the spacecraft continues moving along the adjusted path. Minutes become hours. Hours become days. A slight bend becomes a wide arc. A small decision echoes across millions of kilometers. You can sense this effect by imagining walking across an enormous open plain. If you change your heading by just 1 degree, the shift feels trivial at first. After a few steps, you hardly notice it. But after walking for hours, you end up far from where you would have been. Space magnifies this principle because there is nothing to damp it. No friction corrects the course. No resistance pulls it back. This is why changing direction is often more important than changing speed. A spacecraft does not need to go faster to reach a new destination. It needs to aim differently. Once aimed, inertia does the rest. The spacecraft follows its new trajectory with unwavering commitment. This principle also explains why timing matters so much. A burn performed at one point in an orbit can have a completely different effect than the same burn performed elsewhere. When a spacecraft fires its engine while moving forward along its orbit, it increases its speed and rises into a higher orbit. When it fires in the opposite direction, it slows down and drops into a lower one. The same engine, the same thrust, but radically different outcomes depending on direction. Even more subtle are burns that are angled slightly sideways or upward relative to the orbital plane. These do not primarily change how fast the spacecraft goes. They tilt the entire orbit itself. The spacecraft begins to circle its planet at a new angle, passing over different regions of space. Again, the change may be small at first, but once made, it is permanent unless deliberately undone. What makes this feel almost counterintuitive is how little energy these changes can require. Because the spacecraft already has so much speed, altering its direction is often cheaper than altering its speed. A modest engine burn can redirect an enormous amount of motion that already exists. This is why spacecraft navigation is often described as sculpting trajectories rather than driving paths. Engineers are not continuously steering. They are making a few decisive adjustments and then letting the spacecraft coast along the shape that has been created. Over long missions, this approach becomes essential. Carrying fuel is expensive. Every kilogram of propellant must be launched, accelerated, and accounted for. Precision replaces force. Patience replaces power. A spacecraft that understands how to change direction efficiently can travel farther than one that simply tries to go faster. There's also a deeper elegance here. The spacecraft is not imposing its will on space. It is working with the natural rules of motion. It accepts the speed it already has and asks only that it be redirected slightly. In return, the universe carries that decision forward faithfully without loss or complaint. This distinction between speed and direction also reveals something fundamental about motion itself. Motion is not a single quantity. It has structure, it has orientation, it has history. A spacecraft's path is not defined only by how fast it is going, but by how that speed is aimed at every moment. Seen this way, spaceflight becomes less about force and more about geometry. Paths are curves, adjustments are angles, destinations are intersections of motion and time. The spacecraft moves not by constant effort, but by carefully choosing how its existing motion is allowed to unfold. As these ideas settle into place, the vastness of space feels less hostile and more navigable. The emptiness is no longer an obstacle. It is what allows small choices to matter. In a universe without friction, direction becomes destiny, and a single gentle change can carry a spacecraft across the solar system. Once the difference between speed and direction becomes clear, gravity reveals another, more surprising role. It does not merely bend paths into orbits. Under the right circumstances, it can quietly lend energy, allowing a spacecraft to change its speed without burning fuel. This is not a trick or a loophole. It is a natural consequence of motion shared between massive bodies. When a spacecraft approaches a planet, both are moving. The planet is not fixed in space. It is sweeping along its own orbit around the Sun, carrying an enormous amount of momentum. As the spacecraft falls toward the planet and curves around it, the two briefly become part of the same moving system. From the spacecraft's perspective, gravity pulls it inward, bends its path, and then releases it again. If the encounter is arranged carefully, the spacecraft can leave with a different speed relative to the Sun than it had before. It has not created energy. It has exchanged it. A helpful way to picture this is to imagine throwing a tennis ball toward a massive moving truck. If the ball bounces forward off the truck, it leaves with more speed than it arrived with, having borrowed a tiny bit of the truck's motion. The truck barely notices. Its mass is too great. The ball, however, feels the difference immediately. A gravity assist works the same way, except nothing actually touches. The interaction happens through gravity alone. The planet loses an immeasurably small amount of orbital energy. The spacecraft gains a measurable amount of speed. What makes this especially elegant is that the spacecraft does not need to fight the planet's gravity to escape. It uses the fall and the curve to its advantage. As it approaches, gravity accelerates it. As it departs, gravity decelerates it by the same amount. But because the planet itself is moving, the direction of that exit matters. If the spacecraft leaves in the direction of the planet's motion, it carries some of that motion away with it. From far away, the spacecraft's speed relative to the planet looks unchanged. From the broader perspective of the solar system, everything has shifted. The spacecraft has been redirected onto a faster, slower, or differently shaped solar orbit, all without firing its engine. This technique allows missions that would otherwise be impossible. A spacecraft launched directly toward the outer planets would need far more fuel than any rocket could carry. By weaving past inner planets first, spacecraft gradually reshape their trajectories, building speed step by step, borrowing tiny amounts of momentum from worlds that already have plenty to spare. Timing is everything here. The planet must be in the right place, moving in the right direction, at the exact moment the spacecraft arrives. Years of planning can hinge on a window that lasts only minutes. Miss it, and the opportunity vanishes until the planets line up again. There is a quiet humility in this method of travel. The spacecraft does not demand power. It waits. It arrives when the geometry is right and accepts what gravity offers. The universe rewards patience with efficiency. Gravity assists also reveal something deeper about motion. Motion is not owned by any single object. It is relational. Speed depends on what you measure it against. A spacecraft can leave a planet faster than it arrived without violating any laws, because the planet was moving too. Seen this way, spaceflight becomes a choreography. Planets move. Spacecraft move. Paths intersect briefly, exchange influence, and separate again. No engines roar. No dramatic forces appear. Just quiet, precise redirection governed by conservation and geometry. After the encounter, the spacecraft drifts onward, its new trajectory locked in by inertia. The planet continues on its way, unchanged in any meaningful sense. The exchange is complete, and the borrowed momentum blends seamlessly into the spacecraft's long, silent journey. In this moment, space reveals itself not as empty, but as structured. Motion threads through it. Gravity connects it. And a spacecraft, by understanding those connections, can travel farther than brute force alone would ever allow. After gravity assists reshape a spacecraft's path, there is still an ongoing need for care and refinement. Even the most carefully planned trajectory is never perfectly isolated. Tiny influences accumulate. Radiation pressure from sunlight nudges the spacecraft. Uneven gravity fields introduce subtle drifts. Small uncertainties at launch stretch into measurable deviations over time. In space, precision is not a one-time achievement. It is something that must be quietly maintained. This is where course corrections enter the story. A course correction is not a dramatic maneuver. It is often so gentle that it barely registers as motion at all. A brief firing of small thrusters changes the spacecraft's velocity by a fraction of a meter per second. Compared to the thousands of meters per second the spacecraft already has, the change seems insignificant. Yet, because that change persists, it gradually realigns the entire journey. These corrections are usually planned far in advance. Engineers predict where the spacecraft will be weeks or months from now, and calculate how even the smallest error will grow if left untouched. Then, at just the right moment, a short burn nudges the path back into alignment. After that, inertia carries the correction forward, spreading its effect across vast distances. What makes this possible is restraint. Spacecraft do not constantly steer. They wait, they measure, they intervene only when necessary. Each correction is chosen to do as much work as possible for as little effort as possible. Fuel is precious, and every action must justify itself over time. Alongside course corrections is a related but distinct kind of control: attitude control. While course corrections change where the spacecraft is going, attitude control changes how it is oriented. Orientation matters because a spacecraft is not symmetrical in function. Antennas must point toward Earth. Solar panels must face the sun. Instruments must be aimed precisely to observe their targets. To manage this, spacecraft use small thrusters or reaction wheels. Reaction wheels are particularly elegant. They are heavy wheels mounted inside the spacecraft that spin faster or slower to rotate the spacecraft in the opposite direction. Nothing is expelled. No fuel is burned. Angular momentum is simply rearranged within the system. You can picture this by imagining sitting on a swivel chair while holding a spinning bicycle wheel. If you twist the wheel, your body rotates in response. The same principle allows a spacecraft to turn itself without interacting with the outside world. Orientation changes, but the overall motion through space remains untouched. This separation of translation and rotation is another unfamiliar feature of space. On Earth, turning and moving are often inseparable. In space, they are independent. A spacecraft can rotate freely while continuing along its path, like an arrow spinning gently as it flies, its trajectory unchanged. Attitude control must be extremely smooth. Sudden rotations can blur instruments, disrupt communications, or stress delicate structures. So movements are slow, deliberate, and carefully damped. Sometimes a spacecraft takes hours to complete a turn that would take seconds on Earth. In the silence of space, there is no urgency. Over long missions, even reaction wheels reach their limits. External influences gradually build up unwanted rotation. When that happens, small thrusters fire briefly to bleed off excess angular momentum. Again, the intervention is minimal, chosen only when needed, and then the spacecraft returns to quiet balance. All of this control happens against a background of constant motion. The spacecraft is always moving, always falling through curved space-time, always carrying its inertia forward. Course corrections and attitude adjustments do not interrupt that motion. They simply refine it. What is striking is how little effort is required to remain on course. A spacecraft crossing the solar system may need only a handful of carefully timed corrections. The rest of the journey unfolds naturally, guided by gravity and preserved by inertia. This reveals a deeper truth about navigation in space. Control does not come from domination. It comes from understanding. By knowing how motion persists and how small changes propagate, engineers can guide spacecraft with a light touch. The universe does most of the work. There is also an emotional quality to this kind of travel. Spacecraft do not rush. They do not react impulsively. They respond calmly to slow deviations, trusting that gentle actions taken early will prevent larger problems later. It is a form of patience built into the physics itself. As a result, spacecraft motion feels almost alive in its subtlety. Small adjustments ripple forward, orientation shifts quietly, paths curve gracefully. Nothing jerks or resists. Everything flows. In this way, course corrections and attitude control complete the picture of how spacecraft move. Not through constant force, but through occasional intention. Not through struggle, but through alignment. A spacecraft moves by knowing when to act and when to let motion continue, carried onward by the steady, reliable rules of the universe. As course corrections become smaller and less frequent, a broader pattern emerges. Spacecraft do not succeed by overpowering distance. They succeed by respecting it. Energy in spaceflight is not something to be spent freely. It is something to be protected, measured, and used only when it can echo far into the future. Every spacecraft begins its journey with a strict budget. Fuel is finite. Once it is gone, no resupply is possible. This constraint shapes every decision, from launch to the final moments of a mission. The most valuable resource on board is not speed, but the ability to change speed. Each engine burn is a permanent choice. This reality gives rise to a different philosophy of motion. Instead of asking how fast a spacecraft can go, engineers ask how little they can interfere with its motion while still reaching the destination. The answer is almost always less than intuition suggests. One reason is that speed itself is rarely the goal. Arriving at the right place at the right time matters more than arriving quickly. A spacecraft rushing toward a planet on the wrong trajectory gains nothing from its haste. It will miss, overshoot, or require costly corrections. A slower spacecraft, properly aimed, arrives exactly where it needs to be. This is why many missions take years to unfold. After launch, a spacecraft may spend months or even decades following long, looping paths around the Sun. From the outside, this can look inefficient or hesitant. In reality, it is deeply intentional. These paths minimize fuel use by letting gravity and inertia do the heavy lifting. Energy efficiency in space is tied to the idea of leverage. A small change applied early can replace a large change applied late. A brief engine burn near Earth can determine where a spacecraft will be years later, far beyond the orbit of the outer planets. Waiting too long to make that adjustment would require far more energy to correct. This is another way patience expresses itself in spaceflight. Actions are taken when they are cheapest, not when they feel most urgent. The spacecraft does not rush to fix small errors. It waits until the geometry is right, then acts once, cleanly, and stops. The quietness of this approach can be deceptive. There are moments when nothing appears to be happening at all. Weeks pass. Months pass. The spacecraft sends back routine data, its engines silent. Yet, during this time, it is covering millions of kilometers, its trajectory unfolding exactly as planned. This long view is necessary because motion in space is cumulative. Every decision compounds. An extra meter per second of speed added today changes where the spacecraft will be tomorrow, and the next day, and the next. Over time, those changes grow larger than any single engine burn could achieve on its own. This is also why spacecraft often prefer low-thrust engines, such as ion drives, for long missions. These engines produce extremely gentle thrust, sometimes no stronger than the weight of a sheet of paper resting on your hand. They cannot launch a spacecraft from Earth. But once in space, they can run for months or years, slowly and continuously reshaping the spacecraft's velocity. Each moment of thrust adds a tiny amount of change. Individually, these moments are negligible. Together, they accumulate into speeds far greater than those achieved by short, powerful burns. The spacecraft accelerates patiently, trusting time to amplify the effect. This trade-off reveals something subtle about energy. Power and efficiency are not the same. A powerful engine delivers change quickly, but at great cost. An efficient engine delivers change slowly, but wastes almost nothing. In the vast timescales of space travel, slow efficiency often wins. There's also a psychological shift required to appreciate this. On Earth, speed is associated with progress. Faster means better. In space, speed without precision is meaningless. Progress is measured by alignment, not urgency. This is why mission timelines are filled with long stretches, labeled simply as cruise. During cruise, the spacecraft is not idle. It is exactly where it should be, doing exactly what it should be doing, which is letting motion persist. Nothing needs to be added. Nothing needs to be corrected. Intervention would only make things worse. Even communication reflects this patience. Signals take minutes or hours to travel between Earth and a distant spacecraft. Commands are planned carefully and sent well in advance. Real-time control is impossible. The spacecraft must be trusted to carry out its instructions calmly and autonomously. This reliance on patience changes the relationship between humans and machines. Engineers are not driving the spacecraft moment by moment. They are collaborating with it across time delays, trusting the physics and the planning to hold. There is a quiet confidence embedded in this process. Once the trajectory is set and verified, there is often nothing left to do but wait. The spacecraft will arrive because nothing is acting to stop it. Motion, once given, remains faithful. This patience also extends to arrival itself. Slowing down in space is often harder than speeding up. To enter orbit around a planet or land on a surface, a spacecraft must shed enormous amounts of energy. This requires careful planning, sometimes using atmospheres or gravity itself to bleed speed away gradually. Again, the solution is not force, but timing. Arrive at the right angle. Enter at the right speed. Let natural processes do most of the work. Intervene only where necessary. In the end, energy efficiency in space is not about thrift for its own sake. It is about harmony with how motion behaves. Space does not reward impatience. It rewards understanding. A spacecraft that moves well is not one that is constantly active. It is one that knows when stillness is appropriate. It waits. It listens. It allows inertia and gravity to carry it forward. And when it acts, it does so gently, knowing that even the smallest change, applied at the right moment, can shape an entire journey across the solar system. After energy efficiency and patience settle into the logic of space travel, the idea of coasting begins to take on a very different meaning. On Earth, coasting feels temporary and passive. A car coasts only briefly before friction slows it to a stop. A bicycle rolls a little farther, then falls still. Coasting feels like something that happens in between actions, never something that lasts. In deep space, coasting is not an in-between state. It is the main event. When a spacecraft enters its cruise phase, engines off and trajectory set, it is not waiting for something to happen. It is already doing exactly what it was designed to do. It is moving steadily and faithfully along a path that was carefully shaped earlier. Nothing more is required of it. This can feel unintuitive because we tend to associate motion with activity. We expect sound, vibration, effort. But motion in space is silent. There is no sensory feedback to suggest speed. A spacecraft traveling tens of thousands of kilometers per hour experiences no rushing wind, no engine strain, no external signal of progress. Motion is inferred only through careful measurement and the passage of time. This is why coasting in space is often misunderstood as drifting. Drifting suggests randomness or lack of control. Coasting in space is neither. It is controlled motion, preserved precisely because nothing interferes with it. The spacecraft is not wandering. It is following a trajectory defined by initial conditions and shaped by gravity. Once engines shut down, the spacecraft's future position is already written into its present motion. Every second of travel simply reveals what was already encoded in its velocity and direction. In this sense, coasting is not passive at all. It is the unfolding of a decision made earlier. This idea can feel almost philosophical, but it is grounded entirely in physics. In a frictionless environment, the present contains the future. Change only enters when a force is applied. Without intervention, motion continues exactly as it is. This is why long periods of coasting are not risky by default. They are often the safest part of a mission. With engines off, there are fewer systems active, fewer opportunities for error, fewer variables to manage. the spacecraft becomes a stable, predictable object moving through a predictable gravitational landscape. During these long coasting phases, the spacecraft is still very much alive in a technical sense. Instruments take measurements, antennas point toward Earth, solar panels adjust their orientation. Data flows steadily across vast distances, but its path through space remains unchanged unless deliberately altered. The calmness of this phase is deceptive. While the spacecraft coasts, it may pass through regions where gravitational influences subtly overlap. The pull of the Sun dominates, but planets contribute slight tugs. Over long timescales, these influences gently curve the path. The spacecraft does not resist them. It incorporates them naturally into its motion. From mission control, coasting looks like quiet confidence. Engineers track the spacecraft's position and velocity, comparing real data to predictions. Often, the match is astonishingly close. Days or weeks into a cruise, the spacecraft is exactly where it was expected to be, because nothing has acted to change its motion. When deviations do appear, they are usually small and slow. A tiny misalignment of solar radiation pressure, a slight uncertainty in earlier thrust. These effects are not emergencies, they are anticipated. A correction may be planned weeks ahead, applied gently, and then the spacecraft returns to coasting again. This rhythm defines much of spaceflight. Action, then long stillness, then action again. The stillness is not empty. It is productive in its own way, allowing motion to accumulate distance without cost. There is also an important psychological shift embedded in this idea. On Earth, we are trained to equate effort with progress. In space, effort is expensive and often unnecessary. Progress happens because the laws of motion allow it to. The spacecraft advances not because it is constantly doing something, but because it is allowed to keep going. This reveals a deeper truth about movement itself. Motion is not sustained by force. Force only changes motion. Once that distinction is fully absorbed, coasting stops feeling like inactivity and starts feeling like trust. Trust in inertia. Trust in planning. Trust in the quiet reliability of physical law. A spacecraft coasting through deep space is a demonstration of confidence in the universe's consistency. Engineers are saying, in effect, we have shaped this motion correctly, and now we will let it be. There is something almost meditative about this phase. The spacecraft glides through sunlight and shadow, past invisible gravitational contours, carrying its momentum forward unchanged. Time stretches. Distances compress. Days blur into weeks, weeks into months. Yet nothing about this motion is vague. Every kilometer traveled was implied from the start. Every arrival point is a consequence of earlier choices. Coasting is simply the universe honoring those choices without interference. This is why the phrase engine burn carries so much weight in mission timelines. Burns are rare. They are moments of intention. Coasting is the long fulfillment that follows. Even dramatic encounters, like planetary flybys, are often embedded within coasting arcs. The spacecraft approaches on a trajectory shaped long before, curves around the planet, and departs again, engines silent. Gravity does the work. The spacecraft remains a passenger in a carefully arranged exchange. In this sense, deep space travel is not about constant control. It is about setting conditions and then allowing them to play out. The spacecraft does not wrestle with space. It moves through it by agreement. As this understanding settles, the image of a spacecraft changes. It is no longer a machine fighting emptiness with fire and force. It is a quiet object, given motion once, then carried forward by the simplest rule of all. Things in motion stay in motion. Coasting is not a pause between actions. It is the natural state of travel in a universe that does not interfere unless asked to. And in that vast, nearly silent environment, the most powerful thing a spacecraft can often do is nothing at all. As coasting becomes familiar, one final aspect of spacecraft motion comes into focus, and it is perhaps the most quietly disorienting of all. In space, movement happens without sound, without wind, and without resistance. Nothing announces that motion is occurring. Nothing responds to it. The universe remains silent and unchanged as a spacecraft passes through. On Earth, motion is always accompanied by sensation. Air rushes past. Engines roar. Surfaces vibrate. Even when we close our eyes, we can feel speed through pressure and noise. These cues are so deeply ingrained that we mistake them for motion itself. But they are not motion. They are consequences of moving through a resisting medium. Space removes the medium. A spacecraft traveling at extraordinary speed feels no different from one at rest. Inside, instruments float. Loose objects drift gently. There is no vibration unless something internal creates it. From the spacecraft's own frame of reference, nothing is happening at all. This is not because the spacecraft is isolated from the universe. It is because motion, by itself, produces no sensation. Only changes in motion do. Acceleration can be felt. Rotation can be felt. But steady movement through empty space is indistinguishable from stillness. This realization brings us back to inertia in its purest form. In a universe without friction, motion has no signature. It leaves no wake. It stirs no medium. It does not announce itself. Spacecraft does not carve a path through space. Space closes seamlessly behind it, as if nothing passed through it all. This is why there is no sound in space. Sound requires a medium to compress and rarefy, to carry vibrations from one place to another. Without air, there is nothing to vibrate. Engines can roar inside a spacecraft, shaking its structure, but that sound cannot escape into the surrounding vacuum. The absence of wind follows the same logic. Wind is not motion itself. It is air resisting an object moving through it. Remove the air and the sensation vanishes. A spacecraft can travel faster than any jet ever built and experience no wind at all. Resistance disappears for the same reason. Drag is not an inherent feature of motion. It is the cost of pushing through matter. In space, there is almost nothing to push through. Motion becomes effortless, not because energy is being supplied, but because none is being taken away. This changes how we must think about speed. Speed in space is not something you feel. It is something you calculate. It exists only in relation to other objects. A spacecraft may be moving slowly relative to one planet and extremely fast relative to another. Neither speed produces any internal sensation. This relativity of motion is not philosophical. It is practical. Navigation depends entirely on reference frames. Engineers describe a spacecraft's velocity relative to Earth, relative to the Sun, or relative to a target planet, depending on what matters at that moment. None of these velocities is more real than the others. They are simply different ways of describing the same motion. Because motion has no built-in signal, spacecraft rely on constant measurement. Star trackers compare the positions of distant stars. Gyroscopes detect tiny rotations. Radio signals exchanged with Earth reveal changes in distance and speed through precise timing. Motion is inferred, not felt. This is why spaceflight demands such careful accounting. When nothing pushes back, mistakes persist. A small error in velocity does not fade. It carries forward indefinitely, growing in consequence with time. The universe does not correct it for you. At the same time, this absence of resistance is what makes interplanetary travel possible at all. On Earth, maintaining high speed requires continuous energy input. In space, once speed is achieved, it costs nothing to keep it. The price is paid only when motion changes. This leads to an almost paradoxical situation. Space is vast, but travel through it is energetically cheap once underway. The difficulty lies not in crossing distance, but in leaving places and arriving at others. Escaping gravity wells and entering new ones are where energy is spent. Between those moments, the spacecraft exists in a state that is neither effortful nor passive. It is simply moving, unopposed and unremarked upon by its surroundings. This quality gives space motion a strange purity. There is no turbulence to complicate it, no wear from resistance, no erosion from friction. A spacecraft can travel for decades with its fundamental motion unchanged from the day it left Earth. Even sunlight, which does exert pressure, does so gently. Photons carry momentum, and when they strike a spacecraft, they impart a tiny push. Over long time scales, this pressure can matter, but it is subtle, predictable, and incredibly weak. It does not disrupt motion. It merely whispers to it. In this environment, movement feels almost abstract. Paths exist as mathematical relationships rather than physical tracks. Orbits are invisible. Trajectories leave no marks. Everything is defined by numbers and predictions, not by physical traces. And yet, this abstraction does not make space cold or mechanical. It makes it consistent. The same rules apply everywhere. Motion behaves the same near Earth as it does near the edge of the solar system. Once learned, it can be trusted. This trust is what allows spacecraft to venture so far. Engineers can send a machine billions of kilometers away, knowing that if nothing acts on it, it will arrive exactly where expected. Not approximately. Exactly. There is something quietly profound in that reliability. It suggests a universe that does not interfere unnecessarily. A universe that allows motion to persist, undisturbed, once set in motion correctly. When we imagine spacecraft streaking through space, it is tempting to add drama. Flames, noise, force. But the reality is calmer and more precise. A spacecraft moves the way a thought moves once it has been formed. It continues, unchanged, until something deliberately alters it. In the end, spacecraft motion teaches us something fundamental about the nature of reality. Motion is not sustained by struggle. It does not require constant effort. It does not need an audience or a response. It simply continues. In the silence of space, without sound or wind or resistance, movement reveals its true character. Not as an act, but as a state. Not as something that must be maintained, but as something that endures. A spacecraft gliding through the dark is not fighting the universe. It is participating in one of its simplest agreements. Once motion is given, the universe allows it to remain. Once motion is allowed to exist without resistance, something subtle begins to happen to our sense of distance and time. In everyday life, distance feels heavy. It demands effort. It must be crossed actively. In space, distance becomes something different. It is not an obstacle to be overcome, but a duration to be endured. A spacecraft does not experience distance the way we do. There is no strain associated with covering it, no fatigue, no sense of progress measured in exertion. Distance unfolds simply because time passes while motion remains unchanged. 1,000,000 kilometers is not a challenge. It is just a longer wait than 1,000. This changes how journeys are conceived. Instead of asking how to push through space, mission designers ask how long they are willing to let motion persist. The answer is often surprisingly long. Years are acceptable. Decades, sometimes, because nothing is being consumed by the act of traveling itself. This is why some spacecraft are still moving through interstellar space long after their missions have ended. Their instruments may be silent, their transmitters weak or gone, but their motion continues, exactly as it was left. They have not slowed, they have not drifted to a stop. They are still carrying the momentum given to them long ago. In this sense, spacecraft motion has a kind of afterlife. Once launched, a trajectory never truly ends. It only becomes less relevant to us. The universe does not discard motion when attention fades. There is a quiet humility in realizing this. Human timelines are short. Spacecraft timelines stretch far beyond planning documents and mission phases. A trajectory drawn today may still be unfolding thousands of years from now, long after its creators are gone. This endurance is not special to spacecraft. It applies to everything. Planets continue their orbits. Stars move through galaxies. Galaxies drift through clusters. Motion accumulates across cosmic time because, on the largest scales, there is so little to stop it. Spacecraft simply make this principle visible on a human scale. They show us that movement does not need to be dramatic to be profound. A gentle push, applied once, can echo for centuries. A small decision, made early, can determine positions far into the future. This also reframes how we think about control. Control in space is not about constant adjustment. It is about initial conditions. Get those right, and the rest follows naturally. Get them wrong, and correction becomes costly. There is an analogy here that emerges naturally from the physics. Imagine releasing a note into a long, sustained piece of music. If the pitch is right, it blends and carries forward. If it is wrong, it clashes, and effort is required to resolve it. Spaceflight is about choosing the right note and then letting it ring. This perspective makes the act of launch especially significant. Launch is not just the moment a spacecraft leaves Earth. It is the moment its future is set into motion. Every meter per second matters. Every direction matters. What seems like a brief, fiery ascent contains the seeds of everything that follows. Once beyond Earth's atmosphere, the drama ends quickly. The rest of the journey is quiet. And that quiet is not emptiness. It is clarity. Clarity because the rules are simple. Clarity because nothing interferes. Clarity because cause and effect are cleanly separated. In space, if something changes, there is a reason. A force acted, an engine fired, a gravitational field bent the path. Nothing happens by accident. This transparency is rare in nature. On Earth, countless forces overlap. Air currents shift, surfaces deform. Friction hides inertia. Causes blur together. Space, the simplicity returns. That simplicity is what allows prediction. Engineers can say, with confidence, where a spacecraft will be years from now. Not approximately, precisely. Because the laws governing its motion are stable and universal. This reliability does not mean space is static or dull. It means it is trustworthy. Motion behaves the same way today as it did billions of years ago. The same rules that guide a spacecraft also guide planets and stars. In learning how spacecraft move, we are really learning how the universe moves. We learn that motion is conserved, not consumed. That direction matters as much as speed, that gravity shapes paths without effort, that patience amplifies small actions. And, perhaps most importantly, we learn that stillness and motion are not opposites. In the absence of resistance, motion becomes a form of stillness. A spacecraft moving steadily through space is internally at rest, even as it crosses unimaginable distances. This idea challenges something deep in us. We are used to thinking of movement as change. In space, movement without acceleration is sameness. Nothing about the internal state of the spacecraft evolves simply because it is moving. Time passes, distance accumulates, but the state remains. This is why astronauts in orbit feel weightless. They are not floating because gravity is gone. They are floating because they are moving in such a way that gravity no longer produces internal stress. Motion and gravity cancel out an experience, even though both are fully present. The same principle applies on every scale. Motion does not need to be felt to be real. It does not need to announce itself. It does not need resistance to validate it. It simply exists. When we imagine spacecraft as explorers, we often picture them battling the void. But the truth is gentler. They are guests moving through a universe that does not object to their presence. They follow curves already written into space-time. They borrow momentum from worlds that have it to spare. They coast when no change is needed. They act only when acting will matter. In doing so, they reveal a style of movement that is almost ethical in its restraint. Take only what you need. Change only what must be changed. Let the rest continue. There is a quiet lesson here that extends beyond engineering. Not everything requires constant effort. Not all progress is loud. Sometimes the most effective way to go far is to begin well and then trust what follows. Spacecraft move through space not by conquering it, but by understanding it. They succeed not because they are powerful, but because they are precise. And as they move, silently and steadily, they demonstrate something remarkable about the universe we inhabit. Once motion is given, and nothing stands in its way, the universe is content to let it continue. Endlessly. As that idea settles, another layer of understanding quietly opens. Motion through space does not just reshape how we think about distance. It reshapes how we think about time. On Earth, time is often experienced through change. Shadows move, sounds fade, objects slow down. Motion and time feel intertwined because friction ensures that movement always transforms into something else. In space, motion decouples from change. A spacecraft can move for hours, days, or years without anything about its motion evolving. Speed remains constant. Direction remains fixed. Internally, nothing signals that time has passed. Time continues, but motion does not age. This is why trajectories can be treated almost like objects. Engineers talk about them as if they exist independently, because in a sense they do. Once a spacecraft is placed onto a path, that path persists as long as no force intervenes. Time passes along it, but the geometry remains. This persistence gives space travel a strange stillness. The spacecraft is moving, yet nothing about its motion requires attention. It does not demand energy. It does not erode. It does not tire. Motion becomes background rather than foreground. From a human perspective, this can feel unsettling. We are used to associating motion with effort and time with decay. In space, neither connection holds. Motion does not imply effort. Time does not imply slowing. Instead, time becomes a measure of separation. The longer the spacecraft travels, the farther it is from where it began, not because it is pushing forward, but because nothing has stopped it. This creates a subtle inversion of cause and effect. On Earth, we move because time passes and we act. In space, time passes because motion continues. The action happened earlier. Time simply reveals its consequences. This inversion is one reason long-duration missions feel conceptually difficult. It is hard to imagine committing to a path years in advance and then doing almost nothing while it unfolds. Yet that is exactly how spaceflight works. Decisions are front-loaded. Consequences arrive later. There is also something revealing about how little the spacecraft itself cares about time. To the machine, a year of coasting is no different from an hour. There is no accumulation of fatigue, no sense of waiting. The only thing that matters is whether a force acts. From the outside, we impose milestones. We count days. We schedule events. But these are human overlays on a motion that is indifferent to our calendars. The spacecraft simply exists in motion until something changes it. This indifference can feel cold, but it is also reassuring. It means the rules do not shift with circumstance. Motion does not behave differently because the journey is long. The same principles apply at every scale. This is why understanding spacecraft motion often leads to a broader realization about the universe. The cosmos itself is full of objects in long, silent motion. Stars orbit galactic centers for hundreds of millions of years. Galaxies drift through clusters over billions. On these scales, motion is the norm, not the exception. We tend to imagine the universe as static, punctuated by dramatic events. In reality, it is always moving, almost always quietly. Spacecraft simply give us a way to notice this. They are small enough to feel familiar, yet they obey the same rules as planets and stars. When we watch a spacecraft coast through space, we are seeing the universe behave naturally, without interference. This recognition can soften our intuition about emptiness. Space is not a void that resists movement. It is a stage that allows motion to persist without comment. Its defining feature is not hostility, but neutrality. This neutrality is what allows a prediction to become so powerful. When nothing interferes, the future is a clean extension of the present. A spacecraft's next position is not a guess, it is a calculation. This does not mean uncertainty disappears. Measurement errors exist. Small forces act. But these uncertainties are bounded and understood. They do not explode chaotically. They grow in ways that can be anticipated and corrected. This predictability is what makes navigation across the solar system possible. Without it, spaceflight would be guesswork. With it, a spacecraft can pass within kilometers of a target after traveling billions. That precision does not come from constant control. It comes from trusting that motion will behave exactly as it always has. There's a kind of quiet faith embedded in every mission. Faith not in luck, but in consistency. Faith that the universe will continue to follow its own rules. This faith is not blind. It is earned through centuries of observation and experiment. From falling apples to orbiting moons to interplanetary probes, the same patterns repeat. When a spacecraft moves, it is not testing the universe. It is confirming it. This confirmation happens continuously. every second a spacecraft remains on course is another affirmation that inertia still holds, that gravity still curves paths predictably, that momentum is still conserved. In this way, spacecraft are not just explorers, they are witnesses. They demonstrate that the laws we infer on Earth remain valid far beyond it. There is something deeply calming in that thought. The universe does not change its rules when we leave home. It does not become stranger or less reliable. If anything, it becomes simpler. The absence of resistance removes complications. The absence of sound removes distraction. What remains is a clear relationship between cause and effect. This clarity can feel almost intimate. Motion becomes something you can sit with rather than something you must manage. A spacecraft gliding through space embodies this calm. It is not rushing. It is not straining. It is simply continuing. And in that continuation, there is a lesson that extends beyond physics. Not all movement requires constant input. Not all journeys require constant effort. Sometimes what matters most is how you begin. Give motion carefully. Aim it well. Then allow it to unfold. Spacecraft move through space by trusting that once motion is set, the universe will not interfere without reason. They move by understanding that stillness and motion are not opposites, but companions. They remind us that progress does not always feel like activity. Sometimes it feels like silence. Sometimes it feels like waiting. Sometimes it feels like nothing at all. Yet beneath that quiet distance is being crossed. Futures are being reached. Decisions made long ago are still playing out. In the end, spacecraft motion is not about conquering space. It is about aligning with it, learning its rhythms, respecting its patience. And once that alignment is achieved, movement becomes effortless, enduring, and almost serene. A spacecraft does not force its way through the universe. It moves because the universe allows it to. As the intuition deepens, one more shift quietly completes the picture. Motion in space is not something a spacecraft possesses on its own. It is something defined by relationships. Speed, direction, position, even rest itself only exist relative to something else. A spacecraft is never simply moving or not moving. It is always moving relative to one object and still relative to another. Relative to Earth, it may be receding rapidly. Relative to the Sun, it may be following a smooth orbital arc. Relative to a nearby asteroid, it may be drifting slowly. All of these descriptions are true at the same time. This relational nature of motion is easy to overlook because on Earth we share a common frame: the ground beneath us, the air around us. These give us a default reference that feels absolute. In space, no such default exists. This is why asking whether a spacecraft is really moving can feel strangely slippery. From the spacecraft's own perspective, it can consider itself at rest, with the universe moving around it. The laws of physics do not object. They work the same either way. What matters is not who is moving, but how motion changes. Only acceleration carries physical meaning. Only when speed or direction shifts does something real happen internally. This idea explains why astronauts float. It is not because gravity disappears. It is because the spacecraft and everything inside it share the same motion. There is no internal signal to distinguish falling from not falling. Relative motion vanishes. In this way, a spacecraft becomes its own tiny world, carrying its frame of reference with it. Inside, the universe feels calm and unchanging, even as stars outside slowly drift across the windows. Navigation, then, is the art of managing relationships. Engineers choose which frame matters at each moment and plan accordingly. When leaving Earth, Earth-centered motion dominates. When cruising between planets, the Sun becomes the primary reference. When approaching a destination, the spacecraft begins to care about the target's motion instead. At no point does the spacecraft switch between moving and not moving. It only changes who it is moving relative to. This layered perspective helps resolve another common confusion. Spacecraft do not slow down as they travel farther from Earth. There is no universal speed that fades with distance. Motion does not dilute. It remains intact until acted upon. What does change is relevance. Earth's gravity weakens. Earth's frame becomes less useful. The spacecraft transitions naturally into a solar frame, where its motion continues smoothly, uninterrupted. This continuity is one reason interplanetary space does not feel fragmented. There are no boundaries where rules change. The same principles govern launch, orbit, cruise, flyby, and arrival. Only the dominant relationships shift. Once this is understood, the universe feels more unified. Earth is not a special place with special rules. It is simply one region of space where certain forces happen to be strong. Move away, and those forces fade, but the underlying behavior remains. This realization can be quietly comforting. The laws that guide a spacecraft away from Earth are the same laws that guided it on Earth. Nothing exotic takes over. Nothing unfamiliar intervenes. The spacecraft does not enter a new regime. It simply leaves behind distractions. In this stripped-down environment, motion becomes honest. There is nothing to hide behind. No friction to blur cause and effect. No resistance to absorb mistakes. What you do is what happens. This honesty is what makes space such a powerful classroom for physics. Concepts that feel abstract on Earth become tangible. Inertia stops being a word and becomes an experience. Conservation of momentum stops being an equation and becomes a trajectory. Spacecraft embody these ideas not because they are special machines, but because they operate where the rules can speak clearly. And yet, despite this clarity, spaceflight remains deeply human. Every trajectory reflects choices made by people. Every maneuver is an expression of intention translated into motion. The spacecraft does not decide where to go. It carries decisions forward faithfully. This gives motion a narrative quality without turning it into a story. The path is not symbolic. It is literal. But it unfolds over time, revealing earlier choices in physical form. A course correction made today changes where the spacecraft will be next year. A missed opportunity echoes forward just as reliably. Nothing is erased. Everything persists. This persistence can feel unforgiving, but it is also empowering. It means small, careful actions matter. It means precision is rewarded. It means foresight has real weight. In space, there is no need to overcorrect. There's time to think. There's time to wait. There's time to let motion do its work. This rhythm stands in contrast to many human systems that demand constant input. Space does not rush. It does not pressure. It allows. That allowance is perhaps the deepest lesson spacecraft motion offers. The universe is not actively opposing movement. It is simply indifferent. If something moves according to the rules, it is permitted to continue. No friction asks it to justify itself. No resistance challenges its presence. Motion is allowed by default. This is why the image of a spacecraft gliding through space feels so striking. It represents a rare alignment between intention and natural law. A machine built by humans moves not by struggle, but by compliance with reality. The spacecraft does not need to be strong. It needs to be accurate. It does not need to be fast. It needs to be well aimed. It does not need to keep trying. It needs to trust what it has already been given. In learning how spacecraft move through space, we are not just learning about rockets or orbits. We are learning about how the universe treats motion when nothing interferes. We are learning that movement does not demand noise, that distance does not demand effort, that time does not demand decay, and that, sometimes, the most effective way to travel unimaginably far is to act briefly, precisely, and then let go. A spacecraft moves through space because motion, once created, is remarkably durable. It endures without sound. It endures without resistance. It endures without attention. And in that endurance, it carries with it a quiet reminder of how the universe works when allowed to speak in its simplest voice. Motion does not need to be maintained. It only needs to be understood. As motion becomes understood as relational and enduring, it slowly recedes from the foreground of attention. For a spacecraft, movement is no longer the story. It becomes the quiet condition under which everything else happens. In this state, motion is assumed. It does not need to be monitored moment by moment. Engineers do not ask whether the spacecraft is still moving. They know it is, because nothing has acted to stop it. Instead, attention shifts to what the spacecraft is doing while it moves. Instruments observe. Antennas listen and speak. Power systems manage energy. Thermal systems balance heat and cold. All of this unfolds atop a foundation of steady motion that requires no supervision. Movement becomes infrastructure. This is an unfamiliar idea on Earth. Here, motion is expensive. It demands fuel, maintenance, and constant correction. We are trained to think of movement as an active process that must be sustained. In space, that assumption dissolves. Once a spacecraft is placed on its trajectory, motion becomes background physics. It is as reliable as gravity, as predictable as time passing. It does not intrude. It simply carries everything along. This background quality of motion is what allows spacecraft to become platforms for observation rather than vehicles in transit. A space telescope in orbit is not thought of as traveling at thousands of kilometers per hour. It is thought of as being somewhere specific, stable relative to its purpose. The same is true for probes sent to other planets. During cruise, they are not described as racing through space. They are described as en route, as if the path itself were a place they temporarily inhabit. This language reflects a deeper truth. In space, a trajectory is as real as a location. It has geometry. It has predictability. It has duration. A spacecraft can occupy a path in the same way it occupies an orbit. Once this idea settles, the distinction between traveling and being somewhere becomes less sharp. A spacecraft on a long interplanetary arc is not between places in the way a car is between cities. It is exactly where it should be, doing exactly what it should be doing. This reframing helps explain why so much of spaceflight feels calm. There are moments of action, yes, but they are brief. The majority of the mission unfolds in a state of quiet correctness. Correct motion, correct orientation, correct timing. When those conditions are met, there is nothing to add. This calm is not accidental. It is designed. Spacecraft are built to minimize the need for intervention because intervention is costly. The ideal mission is one that requires fewer and fewer corrections as it progresses, not more. This is why so much effort goes into modeling and simulation before launch. Engineers are not just predicting where the spacecraft will go. They are designing a future in which nothing unexpected needs to happen. When that design succeeds, the spacecraft's motion fades almost completely from human awareness. Days pass with no commands sent. Weeks pass with nothing but routine data. Months pass in quiet confirmation that physics is still doing exactly what it always does. In those stretches, the spacecraft is not idle. It is simply aligned. There is something almost revealing about how comfortable we become with this. At first, it feels strange to trust a machine to move for months without guidance. Over time, it becomes normal. Trust replaces vigilance. This trust is not emotional. It is empirical. It is built on the knowledge that in space, absence of force means absence of change. The spacecraft does not need reassurance. It does not need encouragement. It does not need to be watched constantly. It needs only to be left alone. This realization can be unexpectedly grounding. It shows that stability does not always require effort. Sometimes stability emerges naturally when interference is removed. In this sense, spacecraft motion offers a rare example of negative work. Success comes from doing less, not more. From choosing carefully, then stepping back. This principle scales upward. Planets move the same way. They do not expend energy to remain in orbit. They simply continue along paths shaped long ago. Stars orbit galaxies. Galaxies drift through the universe. Motion persists everywhere because nothing is stopping it. Spacecraft, small as they are, participate in this same pattern. They are not exceptions. They are confirmations. This participation is what gives spaceflight its strange mix of fragility and robustness. Spacecraft are delicate machines, vulnerable to radiation, micrometeoroids, and system failures. Yet their motion is extraordinarily robust. Once set, it is almost impossible to erase. Even catastrophic failures often leave motion intact. A silent spacecraft continues along its path, unchanged, long after communication ends. The mission may be over for us, but the trajectory remains. This endurance can feel eerie. It reminds us that motion does not belong to us. We initiate it, but we do not own it. Once released, it becomes part of the universe's ongoing state. There is also something quietly ethical about this. Space does not tolerate wasteful motion. Every change has a cost. Every adjustment must be paid for with fuel, time, or opportunity. This enforces a discipline that rewards foresight and restraint. Spacecraft do not thrash or wander. They commit. This commitment is visible in how missions are planned around windows and alignments. A launch delayed by minutes can miss a planetary opportunity by years. Not because space is unforgiving, but because motion, once begun, is so persistent. Miss the window, and the opportunity moves on. This again highlights the difference between force and timing. Space does not require power so much as patience. It asks for attention to cycles, alignments, and long-term consequences. In responding to these demands, spaceflight becomes less about domination and more about listening. Listening to orbital mechanics, listening to gravitational rhythms, listening to what motion wants to do if left alone. The best trajectories often look indirect. They loop, linger, and curve. To an impatient eye, they seem inefficient. In reality, they are deeply economical. They allow the spacecraft to move far with minimal intervention. This economy extends to the end of missions as well. Spacecraft are often placed into stable orbits or sent on escape trajectories when their work is done. Their final motions are chosen carefully, not abandoned. Even disposal is a matter of alignment. All of this reinforces a central insight. Spacecraft move through space not by constant assertion, but by sustained agreement with physical law. Once that agreement is reached, movement becomes effortless. This effortlessness does not diminish the achievement. It elevates it. It means the design was good enough that nature could take over. In a way, the highest compliment a mission can receive is silence. Silence from engines. Silence from alarms. Silence punctuated only by data that confirms the expected. That silence is not emptiness. It is success. As we sit with this understanding, the original question quietly transforms. How do spacecraft actually move through space is no longer answered by engines or forces alone. It is answered by a relationship between intention and persistence. A spacecraft moves because it was given motion. It continues because nothing takes that motion away. It arrives because its direction was chosen carefully. Everything else is detail. And perhaps that is the most surprising lesson of all, that the universe, at its largest scales, does not demand constant effort. It demands clarity at the beginning and restraint afterward. Spacecraft reveal this not by explanation, but by example. They move through space by trusting that motion, once set correctly, is enough. They remind us that sometimes the most powerful action is a brief one, and the most profound journeys are carried not by continuous force, but by the quiet endurance of a single, well-chosen change. When motion becomes background, something even quieter emerges. Movement begins to feel inevitable, not in a dramatic sense, but in a steady, almost comforting way. Once a spacecraft is set on its path, the future stops feeling uncertain and starts feeling scheduled. Not because everything is controlled, but because so little is interfering. In space, inevitability is not fate. It is simply the natural consequence of clarity. A spacecraft does not wonder where it will be tomorrow. Its motion already contains that answer. Unless something acts on it, tomorrow is just today extended. This gives spaceflight a peculiar emotional texture. There is anticipation, but very little suspense. Events unfold because they were arranged to unfold. This is profoundly different from motion in environments filled with resistance. On Earth, unpredictability is constant. A gust of wind, a rough surface, a mechanical failure. These forces continuously rewrite the future. In space, the future is rewritten only when something deliberately intervenes. This makes space motion feel almost ethical in its transparency. If something goes wrong, there is a reason, a miscalculation, an unmodeled force, a failed system. The universe does not introduce randomness on its own. It responds only to what is present. This clarity can feel unforgiving, but it is also deeply fair. Nothing is hidden. Nothing is arbitrary. Every outcome can be traced backward through cause and effect. For a spacecraft, this means there is no such thing as fighting space. There is only aligning or misaligning. If alignment is correct, motion proceeds smoothly. If it is not, correction is required, and correction always has a cost. This cost is not a punishment. It is simply the price of change in a universe that conserves motion carefully. Over time, this leads to a particular style of thinking among those who design and guide spacecraft. They stop asking how to overpower obstacles and start asking how to remove them. They look for trajectories that avoid the need for action rather than ones that demand it. This is why some of the most elegant space missions look almost passive from the outside. the spacecraft appears to wander, looping around planets, lingering in wide arcs, waiting for alignments. But this apparent wandering is actually a form of precision. The spacecraft is not wandering, it is refusing to spend energy unnecessarily. This restraint is not timid, it is confident. It reflects an understanding that in space, doing nothing is often the strongest position available. When a spacecraft coasts, it is not exposed or vulnerable. It is protected by the absence of forces. With engines off, it is harder to disturb than when engines are firing. Stability comes from stillness of change, not from active control. This reverses many intuitions about safety and motion. On Earth, stillness can be fragile. In space, stillness of acceleration is robust. It is the default state of the universe. This default state extends everywhere. Even in regions filled with gravity, motion persists smoothly. Gravity bends paths, but it does not consume motion. It reshapes without erasing. This is why a spacecraft can pass near a planet and emerge still moving, still intact, still predictable. The encounter may dramatically change direction or speed, but once the exchange is complete, motion settles again into persistence. Spacecraft spend most of their lives in this settled state. They are not accelerating. They are not decelerating. They are simply continuing. This continuation can feel almost invisible because it lacks markers. There are no mileposts in space, no sense of passing through something. Distance accumulates quietly. To make sense of this, engineers rely on abstraction. Numbers, coordinates, timelines. These tools replace sensory cues. They allow humans to remain oriented even when nothing can be felt. But the spacecraft itself does not need these abstractions. It does not need to know it is moving. Motion does not require awareness. It requires only the absence of interference. This indifference of motion to observation is another revealing feature of space. The universe does not care whether motion is noticed. It does not amplify it or diminish it based on attention. It simply allows it. This can feel almost philosophical, but it is entirely physical. Motion does not depend on witnesses. It depends on forces. When no force acts, motion remains. This principle is so reliable that entire missions are built around it. Spacecraft are sent to places we cannot see directly, on paths that will not be monitored continuously. They are trusted to arrive because the physics is trusted. That trust is earned every time a spacecraft arrives exactly where predicted. Every successful flyby, every precise orbit insertion, every gentle landing after years of travel. Each success reinforces the same lesson. Space is not chaotic by default. It is orderly. It behaves consistently across time and distance. This consistency is what allows spacecraft to extend human presence far beyond Earth without constant support. A spacecraft does not need to be shepherded. It needs to be aimed. Once aimed, it becomes a moving expression of a decision. That decision, encoded in velocity and direction, persists long after the moment of choice has passed. It persists through silence. It persists through darkness. It persists through the long stretches when nothing seems to be happening. In those stretches, the spacecraft is still doing the most important thing it will ever do. It is continuing. This continuation is not dramatic, but it is profound. It demonstrates that the universe does not require constant intervention to function. It requires only that things be set in motion correctly. This has implications beyond spaceflight. It suggests that many systems, when properly aligned, do not need to be forced. They need to be allowed. Spacecraft are among the clearest demonstrations of this idea because their environment strips away distractions. There is no friction to mask inertia, no noise to confuse cause and effect. What remains is motion in its simplest form. In that simplicity, we see that movement is not inherently energetic. It is not inherently effortful. Effort appears only when motion must change. Change is expensive. Continuation is free. This is why spacecraft designers think so carefully about when to act. Every burn is weighed against its consequences. Every adjustment is evaluated for its long-term impact. Acting too often wastes resources. Acting too late wastes opportunity. The ideal is to act once, well, and then let go. This ideal is not always achievable. Uncertainties exist. Corrections are sometimes needed, but the principle remains. Fewer actions, taken with greater understanding, are better than many actions taken reactively. This philosophy emerges naturally from the physics. It is not imposed. Space teaches it, and space teaches it patiently. It does not hurry mistakes. It does not correct them for you. It simply lets them persist until addressed. This persistence can feel harsh, but it is also empowering. It means foresight matters. It means preparation has real value. It means understanding the rules allows you to move far with little effort. In the end, spacecraft move through space not because they are constantly doing something, but because they are constantly allowed to continue doing what was set in motion earlier. They move because motion, once created, is durable. They move because space does not resist them. They move because the universe honors its own rules without exception. And perhaps that is the quietest, most important insight of all. The universe does not ask motion to justify itself. It does not demand sound or effort or struggle. If motion exists and nothing acts against it, the universe simply lets it be. A spacecraft moving silently through the dark is not an act of defiance. It is an act of alignment. And in that alignment, movement becomes inevitable, enduring, and calm. Once inevitability replaces struggle, motion settles into something even quieter. Something that feels less like traveling and more like existing along a line that happens to extend through space. The spacecraft is no longer experienced as a thing going somewhere, but as a condition unfolding over time, a steady presence carried forward by rules that no longer need to announce themselves. Nothing about its movement asks for attention, because nothing about it is in question. The velocity is set, the direction chosen, the influences known. Time passes, distance accumulates, and the spacecraft remains exactly what it was, only elsewhere. This is where motion becomes almost invisible, not because it has stopped, but because it has become perfectly ordinary. The universe does not comment on it. There is no sound to mark progress, no resistance to signal effort, no sensation to confirm speed. Movement becomes a background fact, like the passage of days or the slow shifting of stars. And in that background, something subtle becomes clear. Motion does not need to feel active to be real. It does not need reinforcement or confirmation. It persists simply because nothing is undoing it. A spacecraft crossing millions of kilometers does not experience travel as a series of events, but as a single continuous state. There is no internal difference between now and later, no buildup or release, only continuation. The path does not renew itself each moment. It was defined once, and now it is being honored. This is why spaceflight feels so unlike any other kind of movement we know. It lacks milestones. It lacks effort. it lacks drama. And yet, it is profoundly precise. Every second of motion is exact, every position traceable, every future location implied by the present. In this way, motion in space reveals itself not as something fragile that must be sustained, but as something robust that must only be respected. The spacecraft does not prove its motion by acting. It proves it by remaining unchanged. And as it continues, silently and without resistance, it shows that the universe does not demand persistence from moving things. It offers it. Motion, once set carefully and left alone, becomes one of the most stable states that exists. Motion, at this stage, begins to feel less like an action and more like a form of memory. A spacecraft carries with it the physical record of a moment that has already passed. A launch long finished, an engine burn long concluded, yet still present in every meter it travels. The motion is not being created now. It is being remembered by the universe. Each second of travel is the universe agreeing to keep honoring a decision made earlier, without modification, without commentary. This is what makes motion through space feel so calm and so relentless at the same time. Nothing new needs to happen for the spacecraft to keep going. Nothing needs to be refreshed or renewed. The past is sufficient to sustain the present. This idea of motion as memory is not poetic embellishment. It is a direct consequence of inertia. In a place where nothing interferes, the present state persists as a factual continuation of the past. The spacecraft does not need to check where it is going. It does not need to adjust its behavior to maintain progress. Its velocity already contains its future. Direction and speed are not instructions it follows. They are facts it embodies. On Earth, memory fades quickly. Motion decays. A push is forgotten as friction erases it. Energy leaks away into heat and sound, leaving stillness behind. Space does not erase motion that way. It preserves it. The vacuum acts not as an emptiness that swallows movement, but as a perfect archive that keeps it intact. This preservation changes how causality feels. Cause does not remain behind as effect unfolds. Cause stays present, embedded in the motion itself. The launch is not over just because the rocket engines have shut down. The launch continues, stretched thin across years of travel, encoded into every kilometer that follows. The spacecraft is still leaving Earth, in a very real physical sense, long after Earth has faded into a distant point of light. This continuity collapses the usual separation between action and outcome. In space, outcomes are not sudden. They are gradual revelations. Arrival at a destination is not the end of a journey so much as the moment when a long-established trajectory intersects something new. The path did not change when the spacecraft arrived. The context did. This is why space missions often feel anticlimactic to those expecting spectacle. There is rarely a dramatic final push. There is no surge of effort as the destination approaches. Most of the work was done at the beginning. The end is simply when motion meets its intended reference point. From this perspective, motion becomes less about travel and more about commitment. Once a spacecraft is committed to a path, the universe enforces that commitment with extraordinary consistency. Deviating from it requires effort. Remaining on it requires none. This is the inverse of how we experience a choice on Earth. Here, doing nothing often leads to drift or decay. In space, doing nothing preserves intention. It is change that must be justified. This inversion subtly reshapes how time is experienced. Time no longer feels like something that wears things down. it becomes something that allows things to unfold. A spacecraft does not age in its motion. It may age in its materials, in its electronics, in the slow accumulation of radiation damage, but its trajectory remains as young as it was at the moment it was created. In this sense, motion in space is timeless. Not because time stops, but because time does not act on motion the way we expect. Time passes alongside motion, not through it. The spacecraft moves through space, and time moves through everything else. This separation is another reason why spacecraft motion can feel so abstract. We are used to time and motion being tightly coupled. Faster feels shorter, slower feels longer. In space, speed does not compress or stretch experience. There is no experience of speed at all. Inside the spacecraft, nothing indicates how fast it is moving. A spacecraft moving at orbital velocity feels no different from one drifting slowly. The only thing that breaks this stillness is acceleration. When engines fire, when orientation changes, when gravity gradients become noticeable, then motion announces itself. But once those moments pass, the stillness returns. This stillness is not emptiness. It is a state of equilibrium between past and future. The spacecraft exists in a present that is fully determined by what has already happened and fully predictive of what will happen next, unless something intervenes. That intervention, when it occurs, is never subtle from a physical perspective. Even the smallest engine burn is a sharp event compared to the smooth continuity of coasting. It is a moment where memory is rewritten. The spacecraft's future changes abruptly because its present has been altered. This contrast gives spaceflight its rhythm. Long periods of continuity punctuated by brief moments of change. The change matters precisely because it is rare. When nothing interferes, motion becomes background reality. When something does, everything that follows shifts. This rhythm is not unique to spacecraft. It appears everywhere inertia dominates. Asteroids follow stable paths for millions of years, only to be redirected by a close encounter or collision. Planets maintain their orbits across geological time, altered only by rare interactions. Even galaxies drift along large-scale structures, their motions changing slowly over cosmic epochs. Spacecraft are simply small participants in this broader pattern. Their value lies in making it visible on human timescales. A trajectory that persists for decades allows us to feel, intuitively, how powerful inertia really is when friction is absent. This intuition can be unsettling at first. It challenges deeply held assumptions about effort, progress, and control. We are accustomed to systems that require constant input to maintain behavior. Space is the opposite. Behavior maintains itself unless disturbed. This is why spaceflight demands such careful planning before motion begins. Once a spacecraft is on its way, opportunities for correction exist, but they are constrained. The universe will not slow the spacecraft down to give us time to think. It will not pause to allow reconsideration. Motion continues at the same rate regardless of human hesitation. This does not make space cruel. It makes it honest. It treats all motion equally. It does not privilege intention over execution. A well-planned trajectory is rewarded with effortless continuation. A poorly planned one is punished not by hostility, but by persistence. Mistakes do not fade. They travel. This persistence gives motion a kind of moral neutrality. The universe does not judge. It does not help or hinder. It simply allows consequences to unfold fully. Spacecraft reveal this with unusual clarity because they operate in an environment stripped of distractions. In that clarity, another realization emerges. Motion through space is not directional in any absolute sense. There is no universal forward, no preferred direction. A spacecraft's path is meaningful only relative to what it is moving toward or away from. This relativity means that motion has no intrinsic purpose. Purpose is assigned by context. A spacecraft moving at great speed through interstellar space may be accomplishing nothing of interest, or it may be on a historic mission, depending entirely on where it is headed and why. The physics does not care. Motion remains the same either way. This indifference can feel stark, but it also grants freedom. It means that meaning is something we add, not something imposed. The spacecraft does not need the universe's permission to move with intention. It needs only to obey the rules. Once those rules are followed, the universe does not interfere. This lack of interference is what allows spacecraft to operate far beyond immediate human oversight. Commands take time to arrive. Data takes time to return. The spacecraft must function autonomously, trusting that its motion will remain valid during the long intervals of silence. This autonomy is not intelligence. It is reliance on physics. The spacecraft does not make decisions about where to go. It trusts that where it is going was decided correctly earlier. This trust is built into the hardware itself. Structures are designed to endure long periods of unchanged motion. Systems are optimized for stability rather than responsiveness. Sudden changes are avoided whenever possible. Even the shape of spacecraft reflects this philosophy. They are not aerodynamic because there is no air. They are not streamlined for speed because speed is not experienced. Their forms are dictated by function and stability, not by motion itself. This reinforces the idea that motion in space is not something that shapes objects. Objects shape motion. Once a spacecraft is set in motion, its physical form does not need to adapt to that motion. It does not feel stress from speed. It does not experience drag. It simply exists along its path. This separation between structure and motion is another unfamiliar feature. On Earth, moving faster often means experiencing greater forces. In space, steady motion produces none. This is why spacecraft can be both fragile and fast. Thin solar panels can extend wide without fear of wind. Delicate instruments can remain exposed without abrasion. Speed does not threaten them. Only change does. This again brings attention back to acceleration as the true physical event. Acceleration is where forces appear. Acceleration is where stress is introduced. Acceleration is where energy is spent. Between accelerations, the universe rests. This rest is not inactivity. It is a state of dynamic continuity. Motion persists, but nothing about it evolves. This is why spacecraft designers aim to minimize accelerations. Fewer burns mean less fuel used, less stress on systems, fewer opportunities for error. The ideal mission is one where motion is altered as little as possible after launch. This ideal is never fully achieved. Real missions require adjustments, but the guiding principle remains: change only when necessary. Let continuity do the rest. Over time, this principle has shaped the culture of spaceflight. Engineers learn to think in terms of trajectories rather than maneuvers, of alignments rather than actions. They become comfortable with waiting, with planning far ahead, with trusting long-term predictions. This culture stands in contrast to many other technological domains, where rapid response and constant control are valued. Spaceflight rewards the opposite. It rewards foresight over reaction, patience over urgency, understanding over force. Spacecraft motion is the physical embodiment of these values. When a spacecraft coasts silently through space, it is not idle. It is demonstrating a deep alignment between human intention and natural law. The fact that nothing needs to be done is evidence that something was done correctly. This can be difficult to appreciate in a world where activity is often mistaken for progress. Space challenges that assumption. It shows that progress can be silent, invisible, and effortless once conditions are set properly. This lesson is not abstract. It is written into every successful mission. The long, quiet arcs between planets, the years of cruise punctuated by brief corrections, the arrivals that feel sudden only because nothing announced them beforehand. In these moments, the spacecraft has not changed its behavior. Our perspective has. We notice motion only when it intersects with something. A planet, a measurement, a signal. Otherwise, it remains unnoticed, even as it carries the spacecraft across unimaginable distances. This unnoticed motion is not wasted. It is essential. It is the mechanism by which space is traversed at all. If motion required constant attention, spaceflight would be impossible. The distances are too large, the delays too long, the resources too limited. It is only because motion persists without maintenance that spacecraft can exist beyond Earth. This persistence is one of the universe's quiet gifts. It does not draw attention to itself. It does not announce its importance. But without it, the cosmos would be far less navigable. Spacecraft reveal this gift simply by taking advantage of it. They do not exploit it. They align with it. In doing so, they teach us something subtle but profound. That movement, at its most fundamental level, is not about effort. It is about conditions. Set the conditions correctly, and motion becomes inevitable. Set them poorly, and no amount of effort can fully compensate. This is not a moral statement. It is a physical one. Motion through space is not sustained by desire or will. It is sustained by the absence of opposing forces. Once that absence is secured, motion becomes one of the most stable states available. A spacecraft moving through space is not constantly doing something. It is constantly being allowed to continue. And in that allowance, time stretches, distance unfolds, and the universe reveals a rare kind of calm. Not the calm of stillness, but the calm of continuity. A calm where nothing needs to happen for everything to keep happening. That is what it means for a spacecraft to move through space. Not to struggle forward, but to remember a single moment of change and to let that memory carry it onward, faithfully through the dark. As everything gently comes back together, the question that started all of this feels quieter than it once did. How do spacecraft actually move through space no longer asks for engines or flames or force as an answer. It asks for understanding. A spacecraft moves because motion, once created, does not need to be held in place. In the near absence of resistance, movement is not something that fades. It is something that endures. The push happens briefly. The continuation lasts for years. Engines are not there to sustain travel. They exist to change it. A short burst of thrust reshapes speed or direction, and then inertia takes over again, carrying that change forward faithfully. Most of spaceflight is not powered flight at all. It is quiet coasting, guided by decisions made long before. Gravity does not oppose this motion. It collaborates with it. It bends paths into orbits, redirects trajectories, and sometimes lends momentum through carefully timed encounters. Spacecraft do not fight gravity, they fall with it, shaping that fall into curves that circle worlds or reach for new ones. Direction proves to be just as important as speed. A tiny change, applied at the right moment, can grow into a vast difference over time. Space rewards patience and precision far more than raw power. Acting early and gently replaces acting late and forcefully. In this environment, coasting is not drifting. It is control expressed through restraint. Silence is not inactivity. It is confirmation that nothing needs to be corrected. Motion becomes background, a stable condition beneath all other activity. Without air, without sound, without resistance, movement reveals its true nature. It produces no sensation. It announces itself only when it changes. A spacecraft can cross unimaginable distances while feeling, internally, completely still. All of this rests on a simple agreement the universe consistently honors. When nothing acts on an object, its motion remains exactly as it is. No effort is required to maintain it. No struggle is involved. Continuation is free. So, a spacecraft does not push its way through space. It does not battle emptiness or carve a path. It is given motion once, aimed carefully, and then allowed to continue. The universe does not interfere. It simply lets that motion unfold. Seen this way, space travel becomes less dramatic and more elegant. Not a story of constant action, but of careful beginnings and long trust. Not a fight against distance, but a willingness to wait while distance quietly disappears. A spacecraft moves through space because motion is durable, because gravity is predictable, because direction matters, and because the universe does not resist what follows its rules. Once those pieces are understood, the journey itself feels almost inevitable. A brief moment of force, a long stretch of silence, and a path that carries on exactly as intended.